Yeah, that should be it. Is electron spin-lattice relaxation, which is a subject which is very, very old. And it was even done, everything important was even done before I was born. And when my thesis advisor was still in, I think he was, yeah, no, he was still in primary school or just in, maybe he was just getting into secondary school. So that's really, really very old stuff. And to give you an impression how old it is and how long ago all these things were done, is that the first experiment on electron spin-lattice relaxation, at the time they called it paramagnetic relaxation, and the idea was you got a paramagnetic crystal and you wanted to know how fast the magnetization would follow the field. The first experiment was done in 1937. And the idea that there was a relaxation time is not even in that paper, because Gorter, who did the experiment, saw that it was maybe more useful to describe it as a transport of energy or heat. And it was a really very simple experiment. He had an oscillator. He could to oscillate something, but at a few megahertz, and he looked at the heating of the crystal because of the megahertz oscillator he put on the megahertz magnetic field he put on the sample. The theory was even, and that is in that days, that was the first really theory which more or less explained what the right order of magnitude of the relaxation times was by Kronig in 1939. And 1 year later, Van Vleck did everything, and it's a horribly complicated paper to read, but everything on what you would want to know about relaxation is already in it. Only relaxation in rare earth ions, which was done a little bit later, was done in the 1960s or late 1950s, but that then in 1940, for spin-and-a-half system, basically everything was already known. And a lot has been done since. But basically that is experimental work. ESR was necessary to be able to do good experiments and really get good relaxation times. But by the 1970s, more or less everything was well understood. And it's not crazy that people would say in the 70s, well, this subject is old, already 30 years old, and nobody's interested in it. Please do something else. I'm quite surprised that at this moment, again, there are several reasons to be interested. And one, of course, is dynamic polarization, but I also see that there is interest from people who are doing quantum computing stuff. They want to have, they got spins, the spins are the qubits, and they want to be sure that the information in the spin remains there for a long time. The subject is maybe very old, but it's also a very complicated subject because a lot of different things in solids come together. Of course, you got the spin, but the spin is embedded and the energy in the spin has to go to heat. And what is heat? Heat in a solid is vibrations of the lattice. So to understand relaxation, you also have to get some understanding of these lattice vibrations. These spins are not just laying there as an isolated object in the solid. No, they are in some kind of paramagnetic center. It may be a transition metal ion, it may be some defect, it may be something else, like a trityl complicated molecule, but it is not isolated. And that means that you have to know how it's embedded in that paramagnetic center. And then you got all these different interactions. The interaction between the spin and the paramagnetic center it's embedded in, and then the interaction between the paramagnetic center and the lattice vibrations. And all this has to be taken into account. The result is a very extended bit of theory, and if you want to do it for all different cases that you can think, you could easily fill hundreds of pages in a book. And that is far too much to talk about today. Still, it's complicated what I'm going to talk about. At the end, I will give you a link. There is a pardon?
No, please go on, Tom. Sorry.
Oh, yeah, okay. Sorry about that. At the end, I'll give you a link to a paper I just finished and which is submitted to JMR, the Journal of Magnetic Resonance Open. And it's a long paper, but it gives all the mathematics in detail what I'm going to talk about more globally today. And also this talk, you can find it back on that link. So let's start. I will first talk about the lattice vibrations. Lattice vibrations are various types of vibrations in a solid, and roughly you can divide them in two different types. One is something which is very much similar to sound waves, just long wavelength waves that are determined, frequency and wavelength and K vectors, whatever you want, are by the elasticity of the material. You can describe it very often just knowing the macroscopic elastic parameters. The other type is vibrations inside the molecules or inside the primitive cell or whatever. These are typically vibrations of the bonds between atoms, the bonds within molecules. The spectrum of sound waves is generally continuous. Any standing wave that can fit in a sample is possible, but molecular vibrations are often the discrete spectrum because it's specific bonds between atoms that determine the vibrations. For spin-lattice relaxation, the sound waves are the important ones because these have the low frequencies the low frequencies that corresponds to the Zeeman splittings of the electron spins. So the sound waves are the important ones. The molecular vibrations, unless you go to really high temperature, say room temperature or higher, are generally not that important. Above, say 100 Kelvin, yes, then maybe they play a part. But below that, they don't play a part. So I'm going to talk mostly about these acoustical modes, as you call it, which are simply the sound waves. And the sound waves, that's the upper formula here. You see that is a standard oscillating or a traveling wave with a K vector K and with a frequency omega J, and they travel through the sample. The kinetic energy is simply the kinetic energy of the atoms, so it's proportional to the speed or the velocity of the atoms and, of course, the mass of the atoms. And the potential energy, that is something to be a bit careful about. Its elasticity is not the total distance at which an atom displaces. No, it's the relative distance between atoms which determines it. Because if you put two atoms closer together, then you have really create energy. So it's something which is not really the displacement, but rather the relative displacement, which is the derivative of the displacement times the distance between atoms. That is something, and that is not coming down early, but much further in my talk, you will see that. Now, for relaxation, this is all nice classically, but spins are quantum beasts, and you want to have this quantum beast connecting with these sound waves, and that means we have to describe these sound waves as in quantum mechanically. Now, this is done can be done in a very nice, even abstract way. If you look at the sound waves, you can say, well, I got possible standing waves in my material. And depending on the wavelengths, I can put in more or less of these standing waves in it, but they are the number of possible of these standing waves is determined by the size of the crystal. And the energy in that standing wave, you can describe it as a kind of harmonic oscillator. It's the kinetic energy, which he already saw above, times some constant times the displacement squared. And so that's a kind of harmonic oscillator. That means I can replace this Hamiltonian classical by a quantum mechanical harmonic oscillator. So then suddenly I got this, the kinetic energy becomes the derivative to I. And then I got already something which looks like it. And then it's, well, this is the displacement of each atom separately, but that's not a really interesting thing. The interesting thing is more or less the general displacement everywhere. So I'm going to take the Fourier transform with respect to space. So that is basically this Q here is the Fourier transform, and that means the amplitude of each of these waves. And then I get a standard Hamiltonian, which you see very often in, well, you can see them in almost any quantum mechanical book on quantum mechanics. A Hamiltonian in which I got the second derivative of this displacement, which is basically the amplitude of the wave, and an potential, and which is the omega, which is still the frequency of the harmonic oscillator, times this amplitude squared. That is a standard quantum mechanical textbook problem, so I can let loose everything which everybody can find back in quantum mechanical books. So what do you see? Well, in quantum mechanical books will give you the wave functions you see here to the right, and the wave function is basically what replaces the movement. Instead of having a particle moving up and down like this, you get a probability which is determined by the wavelengths to find the particle somewhere along this horizontal line. That is on this position. And that these wave functions, of course, are all just standard quantum mechanical textbook stuff. Now, if you go slightly deeper into this stuff as it is presented in the textbooks, then they often introduce two operators, an operator which I call the creation operator, and I can't explain at this point, but at the next slide I'll explain to you why we call it the creation operator, which is a linear combination of a part which has the Q proportional to Q, which comes out of the potential energy, and something which comes out of momentum, and the second operator, which is not a difference, but which is the sum of these two parts, and which is called the annihilation operator. Now, if you look in these textbooks, then they introduce these two operators, and they put them in the Hamiltonian, and the Hamiltonian gets a simple form. It's the frequency, h bar times the frequency of the oscillator, the creation operator times the annihilation operator plus a half. And the nice thing, and that's the reason why it's often presented this way, is that this product here has eigenvalues, which are integral numbers, 1, 2, 3, and so on. And so that means that the energy levels of the harmonic oscillator is h bar times the frequency times n, which may be 0, 1, and so on, plus a half. And that is a very elegant way of calculating that the energy levels of a harmonic oscillator. Now, why do we spend so much time on this subject, well, that is the next step. The next step is, and that is not in all the quantum mechanical books, but that is a step which is known as second quantization, and that's a very nice way of a very cryptic way of saying things, but the idea is very simple in principle. What do you say? I say I got a harmonic oscillator. The harmonic oscillator is in the state Nj, which means it's on the level, Nj's level of that harmonic oscillator. And that means that the energy is Nj times h bar omega, and well, there's another half, is it? But I just forget about the half. So the energy is like that. Now, then I just say, and that is just a matter of definition, that that's in that state, the harmonic oscillator contains Nj phonons. So if the harmonic oscillator is in the state Nj, I say it contains Nj phonons. And that means I divide the energy, the total energy, Nj times h bar omega, I divide it in n portions, which is each equal to h bar omega. And each of these pieces, I call them a phonon. Now, what happens now if I take this creation operator? I let this creation operator operate on the state Nj. Well, what happens? It becomes the state Nj plus 1. And that's just a matter of doing the math of the harmonic oscillator. And so the number of phonons, which is here Nj, becomes Nj plus 1. So I create a phonon. And if I take the annihilation operator and let it operate on Nj, and I do the math, then I get in the state Nj minus 1. So the number of phonons decreases by 1. So that's the reason why I call this a creation operator. It's actually a phonon creation operator. And this is the reason I call this operator the annihilation operator. So that's one thing. There is more to it. If you take the harmonic oscillator and all the phonon modes, all these lattice modes are independent of each other, they're distinguishable, so they simply follow Boltzmann statistics, and simply the probability of finding you a certain energy is given by this Boltzmann exponential factor. Now let's calculate the expectation value of the number of phonons. So the statistical expectation value of this number. Well, then you have to do a bit of math. You have got this Boltzmann statistics, you multiply it with n, divide it, you normalize the whole thing, and you go through the mathematics, and you find it's 1 over e to the power beta L omega j minus 1. But that's Bose-Einstein statistics. So what did I find? If I call, which is simply calling it, say that phonon, an excitation with a step 1 in the harmonic oscillator, and call that phonons, then these animals that are called phonons are bosons because they obey Bose-Einstein statistics. I go one step further and I look at the acoustical modes, and remember they are standing waves which can be which have a k factor and a frequency. Then if I look at the volume and I look at the density of these modes, then it appears this density is proportional to the k squared. That is a matter of doing the sums correctly. K is the wave factor, and because k is a wave factor, it's a solid and it's an acoustical mode, the propagation speed of this wave is just the sound velocity. then K is equal to the frequency squared divided by the frequency squared divided by the velocity squared, but also the decay is the change of the frequency divided by the velocity squared. So I get the number of modes is proportional to, per unit of frequency is proportional to omega squared divided by v squared. There are two transverse modes. There's one longitudinal mode. I add them all up. I add it up with Bose-Einstein statistics, and I look at the total expectation value per unit of frequency in that sample. Now, what do I get? I get something like omega squared 1 over the frequency, velocity squared to the third power, and this Bose-Einstein statistics. I plot it, and I get this nice function here. Well, that's interesting because that's exactly Planck's radiation law. The only thing to change it to Planck's radiation law is to change the velocity. Light doesn't have a longitudinal mode, so that one I can skip. And here I put the velocity of light, and I got Planck's radiation law. So phonons behave exactly the same as photons. The only difference is that I got also longitudinal modes. And of course, the other difference is that they're extremely slow compared to photons. But they behave exactly in the same way. They're really the same kind of bosons as photons. Well, this is what I want to tell about the phonons, about the lattice. Then I want to say something about the paramagnetic centers. And here is another theorem which is very important and which I just want to explain. And that theorem is due to Kramers, also something in the 1920s, I think, so that's already 100 years ago. But it's a very interesting thing, and that has to do with time inversion. If I have a source here of a magnetic field, a current which goes in a circle, and it produces a magnetic field. And if I invert time, then of course the current goes in the other direction, in negative time direction, but that means that also the magnetic field goes in the other direction. If I have, however, an electric field, then it's just caused by a charge or by a dipole moment, and that is, there's no movement whatsoever. So if I invert time, nothing changes. So the electric field remains in the same direction. Now, Kramers' theorem is that energy should be invariant for the inversion of time. But then a product of an electric field and a magnetic moment, whether it's a spin or an orbit or whatever, can never be part of energy. That the energy of that product should be zero. That means a spin has no interaction with an electric field. And that is the basic thing. And that is a problem for the spin if it wants to relax, because the atoms and the lattice in which it is embedded has electric fields only. So it needs some way to find a way to relax. Well, it has two interactions. One is, of course, the same interaction with an external field, and that is that of the free spin, but it causes a second interaction, and that is a spin-orbit interaction. The paramagnetic center may have a magnetic moment, or anyhow, it may have an orbital moment, and the magnetic interaction between the orbital moment and the spin, that is a magnetic interaction, and that can be an intermediate between the spin and the orbit. So let's go on. Typical situation of two paramagnetic centers. One is a copper 2+. I put it because in the very end I got an experiment showing something about Cooper 2+. Again, that is a system which has spin 2 or orbital momentum 2 and spin 1/2. The same Kramer's argument says that all these levels which you get, which are due to its surroundings by the waters around it, all these levels cannot, they are caused by an electric field, so they cannot split states in the sense that the plus Z is +2 state and the LZ is -2 state. They have to have the same energy. So these are all states in which the expectation value of the LZ is equal to 0. Same, I got trityl. Trityl is somewhat simpler. Typically L is 1. And then I got 3 levels, but again here, the expectation value of the angular momentum is 0. So that's, again, no way for the electron spin to relax. However, there is still matrix element of the angular momentum between these two levels. And between these two levels. And that is the pathway for the electron spin to be able to relax. Now, before I go to relaxation, everybody knows that the Zeeman splitting of a radical or of a transition metal is not equal to exactly the 2 of a free electron. It is slightly different. And that difference is due to the same spin-orbit interaction. A spin-orbit interaction is generally an interaction which is just the dot product between the spin and the orbital momentum, and that has no matrix elements in the ground state, but it has matrix element between the lower. So here I got the high spin and the low spin state in the low orbital state. Here I got the high and the low spin state of the higher orbital state. Then the orbital momentum, the spin-orbit interaction has interactions which couples this low spin high orbital state with this high spin low orbital state, and also the other one here. And that causes in second order, not directly, but in second order, a shift of the Zeeman splitting. And that shift is equal to the ratio of the spin-orbit coupling divided by the splitting between the orbital levels squared. And that is the cause of the bigger Zeeman splitting. Now, I'm finally getting to the spin-lattice relaxation. Well, not really yet, because the orbit has to interact with the lattice. And that is, again, well, how does it work? And now I come back to where I was in the beginning. I got a paramagnetic center. I got 2 atoms in its neighborhood. And because there is this wave coming through it, the distance between the orbital, between the paramagnetic center and its ligands, these 2 other atoms, changes. And that change, that causes changes the energy of the paramagnetic centers a little bit. Again, you have to do the sums, and I'm going rapidly through it. It's the change as a function of the distance. The orbit-lattice interaction is then proportional to that change in distance, which is proportional effectively to the frequency. I go to Phonon operators, and in the end I get an orbit-lattice interaction. But again, because of the Kramers, this is not immediately interacting with this, has no matrix elements between the orbital states. It only has within one orbital state. It only has matrix elements with higher orbital states. So now I'm finally can get to the point that I can tell something about the spin-lattice interaction. So what do you have got? I got an orbital energy, I got a Zeeman energy, and I got a lattice energy of a mode. I got an interaction between the orbit and the spin. So that's an interaction between these two, which is a spin-orbit interaction. I got an orbit-lattice interaction, which is an interaction between this one and that one, which is contained. And then I got a problem that these two interactions don't have matrix elements between the spin states. Oh, this is going too fast. So I need something, a higher excited orbital state. So what is typically then happening? I got here the high spin, low orbital state, which is coupled, for instance, by the spin-orbit coupling to the low spin, high orbital state. And I got the high orbital low spin state, which is coupled by the orbit-lattice interaction to the low spin, low orbital state. And this coupling in second order couples, the latter one couples to the lattice, to the phonon mode, and that couples to creation or annihilation of a phonon. So for instance, by coupling this state with that state and then with that state, I can make a transition of the electron spin down and creating a phonon. And the result is a kind of interaction, which I can put as a term in the spin Hamiltonian, which contains, say, for a creation, say, the spin going up and annihilation of a phonon, or the spin going down and creation of a phonon. And that process is proportional to the spin-orbit interaction and the orbit-lattice interaction. And because it's second order, here in the denominator, there is this splitting squared. Similarly, I got another process, and that is the Raman process. And in the Raman process, it's more complicated because the Raman process involves two phonon modes. If I directly go to the formula, then you will see if the spin goes up, then also a phonon is created in one phonon mode, and another phonon is annihilated in another phonon mode. If I look here at this picture, the spin goes up, and this one goes up, and that one goes down. And this term here, the spin goes down, and the phonon mode goes down, and that one goes up. So here a phonon is annihilated, there's a phonon is created while the spin goes down. So here the spin goes down, and that phonon goes down, and that phonon goes up. But it cannot do directly, it needs other interactions. And first, in this case here, it's the spin-orbit interaction coupling the high spin state with the low spin state in the excited state. Then the orbit-lattice interaction coupling again the low spin state to still a higher orbital state, and then the orbit-lattice interaction couples that one to the low spin state here. So that's a complicated thing. And you see it here in the interaction constant. I got a spin-orbit interaction and the orbit-lattice interaction with one phonon mode and the orbit-lattice interaction with the other phonon mode. Now, this is highly complicated because this is only one possibility. In fact, there are 12 different possibilities of doing that, so you get a lot of terms here. It becomes very complicated, and I won't bother you with that, but the basic idea is that I got this type of terms where I got creation of a phonon, annihilation of a phonon, and simultaneous flip of the nuclear electron spin. Now, let's go and put everything together. What do we see? Well, let's see. I got a G value. The G value differs from 2 because it is the spin-orbit coupling. and the difference is spin-orbit coupling squared divided by the separation between orbital levels squared. Here I got a direct spin interaction, which I just explained. Spin up, spin goes up, photon is annihilated, or the other way. And here I also see the orbit, spin-orbit coupling and this gamma 1. Well, this ratio here is effectively just the square root of the difference in G value. So basically, this interaction is proportional to the square root of the difference in G value. Now I go to this Raman spin-lattice relaxation term. You see the spin go up, a phonon is created, another phonon is annihilated, or something the other way around. Again, I see the spin-orbit coupling coming here. I divide it by the splitting to that spin-orbit. Again, this is the square root of Gs minus G0. Then, to make that into a transition rate, I need to do something with the photon creation annihilation operators. First, I calculate the matrix element, standard quantum mechanics. Then I say, well, I'll go, now they are expressed in the number of phonons. I do boson statistics for the number of phonons, simply put Planck's law here. And then I do a lot of calculations, which I'm not going to show here. And the end rule, what I get is that the relaxation rate is proportional. Well, the interactions come in squared, so it's proportional to the G, change of the G value compared to zero, to that of a free electron spin. Then there is a term which is due to the direct process. Important is that it goes very rapidly with the magnetic field fifth power. It may go, if the polarization is low, it may be, this is the electron spin polarization in equilibrium, which is in the denominator. There is some field dependence there and some temperature dependence there. But the field dependence, very strong field dependence, is the very important thing. And this is the Raman process. Oh, sorry. The Raman process. And well, this is an integral, and I won't go anywhere deeply into that integral, but it has to do, you have to sum over all the phonon modes, and that gives this kind of integral. This part here, for instance, comes from the boson statistics part, but the important thing is a very steep temperature dependence and no field dependence. That is the important thing. And now, let's try to finish this off and just show some experiments. And this is, well, I would like to present it as a random choice, but it isn't a random choice. I've been looking around a lot of the electron spin lattice relaxation time measurements that were done in the 1950s, 60s. A lot of them is bad work because nobody was taking care of getting really clean crystals. So I took one which was done in Leiden, of which I'm absolutely sure that the guy did a good job. Unfortunately, he did it just before people said relaxation made no sense and nobody should work on it, so it was only in his thesis, but then I still got his thesis. And he did T1 measurement from 0.4 Kelvin at X band up to 12 Kelvin, and these are the data points in a very diluted crystal containing copper 2+ ions. Copper has well, a G value which is quite different from that of a free electron. The difference is about 0.2 on average. The other experiment that was done far more recently, 11 years ago, by Lumata and Matthew Merritt, and that was done in high field. And these experiments are very rare. Good experiments in high field are hardly done yet. And they are very interesting because the direct process is very strongly dependent on the magnetic field. He did experiments on tritils, and the experiments here, these are done on 95 gigahertz. These were done on 240 gigahertz, and these, the white points, were done at 336 gigahertz. Now let's try to analyze these experiments. And this is directly done. This was easy because it's a very precise experiments. And you can extract from these experiments the constants A and R, and also the limit. This is the upper limit of the acoustical modes, which is called the deviation limit. And you can extract these things out of it. And then, okay, so this works nicely. This is the direct process, and this is the Raman process, and that fits perfectly well. Then I tried it here, and, well, it didn't work that well. So what I did was, oh, let's suppose that this AD and this AR are just universal constants. Orbach said something like that in the paper. Not very, he didn't argue why, he only said, oh, it works so nice. Just literally is what he says in his paper. Okay, let's do that. Let's assume it the same. I did that. I took the G values, I took the B's, and the same concept. Well, these are the curves. This is not too bad because they're quite close to the experiment. And so maybe Orbach was right. Maybe these two constants are quite universal. Well, let's hope so. Maybe I had a lot of luck here. But anyhow, the direct process is about 5 orders of magnitudes faster in this case. And the Raman process with the T to the 9th is also very, so there must be some truth in what Orbach has said, but well, he isn't around anymore to tell me why he says it fits so well. And he refers to his thesis, and I don't know how to get to his thesis. Okay, that's it. As I promised, this is a very complicated subject, and I've been through it far too fast, and so it's very, I understand fully that people are who really want to know about it, want to know more. I just submitted a paper to JMRO, and it's under review at the moment, and that gives in detail all these relaxation stuff that I've been talking about. And if you want to have a look at the paper, at this talk, you can also get it. Both you can get if you look here at this website. This is my personal website, which is wenckebach.net. And there's HTML, and then there's DNP papers with HTML. You can find it. If you just go to the website, you can automatically you can find this as well. And at the bottom of the list of papers, there is this submitted paper to JMRO, and which is still under review. So maybe you have to change it, or I don't know what the reviewers will say. Maybe they say it's all crap. But anyhow, whatever they say, I put it here, and so you can have a look at it to get some more information. And at the same point, there's a link to this talk. Well, I talked a little bit longer than I promised, but it's still well within the hour, so I hope people are free. Yeah.
Very good. Clap, clap, clap. Thank you, Tom, for the wonderful talk.
Well,
Was not an easy subject. But I just have a question, if I may. A
yeah.
very broad question. I didn't get where exactly the temperature has an influence. So does it have an influence on the phonon modes? Because I didn't see it in the Hamiltonians or the equations.
Well, you don't see it in the Hamiltonian, but you see it in the boson distribution.
Okay.
Let me get back to the temperature comes in the phonon modes, of course, the energy levels of the phonon modes, well, if we go here, the temperature is in the Boltzmann statistics of the occupation of the levels of the phonon modes. And that's basically the number of phonons in a mode. And then if I go to the Planck's radiation law, then this is the number of phonons in a mode with a frequency omega. So if this is the frequency of the phonon modes, then this curve gives you the number of phonons with that mode. And that's the way the temperature comes in.
Okay, thank
And
you.
this assumes that this goes to infinity, which effectively it doesn't do, because acoustical phonons cannot have a frequency which is so high that the wavelengths become shorter than the distance between atoms.
Yes.
Yeah, but anyhow, but that's where the temperature comes in.
Thank you.
Yeah.
We have a question, a first one from Reykjavik. So the first one is, in the Bose-Einstein statistical phonon, which velocity component is more dominating between the transverse or the longitudinal? And are they of similar order, and hence can they be averaged?
Well, actually, that's a good question, because if you look at here, it's now right in front of us, so that makes it easy to answer this. If you look at the velocities of transverse and longitudinal waves generally have a higher velocity of the order of 50%, and sometimes twice as high as the transverse waves. That to the third power makes this a much smaller quantity than this power. And there are also two transverse waves. So basically, this term is about 10 times as strong as that term. So the number of transverse waves and the number of phonons and transverse waves is much larger. On the other hand, it's not immediately obvious that that is also correct for the spin-lattice relaxation, because transverse waves give displacements in a different way. In a longitudinal wave, the atoms come closer together and get further apart. And that is and that may give a bigger change of the potential at the paramagnetic center. And in the transverse waves, it's well, you can think of it as a kind of rotation. The two atoms rotate a bit around each other, and then the potential might change a little bit less. So it's not directly obvious that the transverse waves are also giving bigger spin-lattice relaxation. But in first order, I would say yes, the transverse waves are dominant.
Okay. We have a second question from Reykjavik still. What is the effect of Jahn-Teller distortion in the orbital lattice interaction? More specifically, does symmetry plays a role in determining contribution of orbital lattice interaction to the T1s?
Oh, that's a long question. Just let me. What is exactly? It's about this slide. No, this is the same as splitting. It's more about this slide. So maybe you can repeat the question, please.
Yes, yes, it's about this slide.
Huh?
Yes, it's about slide 10.
Yeah.
Also, Tom, you can see the questions in the Q&A channel. You can read it.
Oh, okay. That is.
Yeah, it's easier.
Yeah. Oh, yeah, I see it. Jahn-Teller distortions. That's the idea. Yeah. That depends largely on the kind of system. In the copper compounds I was talking about, the Jahn-Teller distortion is huge, and that means that the energy splittings due to the Jahn-Teller distortion are so big that they they're just part of the orbital splittings part. There is, however, but that's a detail which in the same thesis of this Leipart I was talking about, there is talk about pairs of coppers, and there are other situations where maybe the Jahn-Teller splittings are somewhat smaller, and then they might play a role. And then you get a kind of relaxation which looks like the Orbach process, which I didn't talk about, which has an exponential temperature dependence. And then, basically that is a whole subject which I just walked quietly around, to be honest. Sorry about that, but yeah, is that sufficient? If
Okay.
yeah, it's yeah.
Yeah, we will proceed with the questions. So we have a question from Frédéric Menting-Vigier. He
Yes.
said, "Hi Tom, excellent talk. And I really
Mm.
thank you for presenting so concisely. It's true. Every time you give a talk, it's mind-blowing how accessible you can make these very complicated notions." So the questions of Fred, the GS, index S, you took here is the average one, GS minus GO, 0.2 in the case of copper.
Well, he is absolutely right.
Mhm.
And this is a very rough analysis, and I'm actually contemplating of doing this analysis much more precisely. And the experiments that were done, which I talked about, were done in a certain orientation, and the relaxation time was measured in a certain orientation of the magnetic field. And I could really imagine that there's an anisotropy in the T1, and I think actually there was an anisotropy in these copper salts, but I have to look that up. The choice of the direction was rather a practical situation of that the spectrum of the copper salt was nice at that direction. But yes, this is a point that has to be looked into.
Okay. So maybe you can see it. We have another question from Quentin Stern. He said, "Great talk."
Let me
Yeah.
see.
So do the dipolar interactions between electrons influence this direction?
Yeah. That's a very good one. Which I didn't show is that reasonably long before Van Vleck and Kronig produced this theory, that is sometime even before Harter did his first experiment, there was a guy named Waller, and he proposed that electrons would relax because of modulation of the interaction between the electron spins and dipolar interactions. Exactly this. And he did calculations. He even proposed a direct process, and he proposed a Raman process and did all the sums on it. So that part of the derivation was already done by this guy Waller. But he had a tiny problem, that the relaxation times he got out of it were about four orders of magnitude too slow. So it wasn't in accordance with the experiments. In a later stage, if you go to, say, concentrated samples in which there are lots of interacting spins, and you got not only dipolar interactions, but also maybe contact interactions, it's still thinkable that that this kind of process will do something, and especially in weak magnetic fields at very low temperature. If you go to very weak magnetic fields, you got this temperature to the field to the 5th power, and if you go to a weak field, it is the 4th power, but it's still very strong. And you go to a weak magnetic field, say at 0.1 0.01 or 10 millitesla, the relaxation time would become hours, according to this Van Vleck mechanism. And in all experiments, you see that it doesn't do that, it flattens off. And there was someone named Temperley who, just in the same time as Van Vleck and Kronig, wrote a paper in which he did predictions of relaxation times in these very concentrated samples, and that he proposed that maybe still there this kind of dipolar or contact interactions, exchange interactions might give some kind of relaxation. It's if I look at measurements that have been done, it's very difficult to decide, if I got a pair of spins, to decide what is the origin of the fast relaxation that you often see in pairs. In this copper salts, it was supposed by Leibhardt to be due to some kind of Jan Teller effect, but there are many other possibilities for pairs to relax rapidly, and yeah, one of the problems is all these old experiments are not very good. You can't trust them all there. So yeah, but so yes, Quentin is right, but I don't know whether this is. I can't give really answers and show cases where this may play a role. Yes.
Okay. There is another question. I will read it out loud for the sake of the recording, Tom. So a question from Yunyao. He has a very specific question. If, imagine we have a C60 in the crystalline and it has one minus charge, how does the rotation of the C60 contribute to the spin relaxation in the theory here?
Yeah. Yeah. Now, the first thing is, where is the electron, the unpaired electron on the C16? Is it free moving along the whole C16? Or is the spin distributed over the whole C16? Or is it a free electron inside the cage? That's the first question, because what I didn't cover here is the case of a free electron in a cage. For instance, F centers in a crystal, then you've got a vacancy, and the vacancy is filled by a free electron, and that has spin half. And then, yeah, what is the orbit, and how does it couple to the orbit? And then the atoms around it. That is a situation which is maybe not so easily answered using the way I approached it here. And spin-orbit coupling, for instance, in the case of this F center, this electron itself, which has the spin, is in an S state, so it has no angular momentum. So where does it get its spin-orbit coupling from? It has to get it from neighbors. And so it's a much more complicated situation than we got here. The result is, that is correct for F centers, that F centers have a very weak spin-orbit coupling and they relax extremely slowly. So, yeah.
Okay.
It's, yeah, what I said at the beginning, you could easily fill a monograph with this subject, because there are so many different situations in which you can have an unpaired electron spin. And then, of course, in the transition metal atom, transition metal ions, it's not just spin and half, but you got much larger spins, and then you got even spins, and then the whole story about Kramer's Kramer's theorem becomes different. There are lots and lots of different situations, and that's too much. Anyhow, for today. But even for that paper I just submitted.